Lavas, hello everybody. I want to go over the workflow of, I think, a more rational way of generating these XenaForms. I will share my screen and I will do this in English, and then I'll translate in Lithuanian for the workshop. Išversiu jums tenais būdamas. Okay, so what we're looking at in the upper left is an artificial intelligence image of a xenoform. I'll explain how I got that later. Going into artificial intelligence is really fast. Coming out of artificial intelligence and redesigning it, I have not figured out fully yet. I don't think there's an automatic way of doing it. We've tried Meshy.ai, MESHY.ai. I've written Python scripts. Um, I think for now we're going to do a manual exploration, but I want people to automate it and be creative. This is an open source studio here. I'm sharing all my secrets. You share your secrets, and that's how we learn. Okay, so now what am I doing here? I'm looking at the AI image and I want to sort of recreate it. So I'm starting to think, well, maybe I'll put some dots around the border, and those dots are these dots here, these red dots. I'm using red so that I would remember something. Those are going to stay on the ground. The other nodes will be up in the air. These will stay on the ground. Okay, so keep an eye on the AI. I thought that was pretty funny. All right, the next thing, I'll explain this in extraordinary detail, but most of the architectural engineering students at Cal Poly know that you need three struts to support a point in space. Thus, the blue dots here are going to be lifted up in the air. The blue ones will be lifted up in the air. So I need three struts for each blue dot. And the three struts go down to the ground because we have the foundation at the ground. Three, not four, not two. It has to be three, but they must connect to the red dots on the ground. Okay, so far so good. I think you could also see how we might be able to do this in Grasshopper. We start to see this pattern. The next thing is that we want to take some time to look at the scale of the problem. How big is this? How big is this span here? How big is this opening here? This is going to be the opening of the shell. How deep is it this way? That will be perhaps this side here, right? So you need to look at your AI image, look at your 2D image. This is in plan view. We are looking down. We're looking down on the structure in plan view. All right, now the magic starts to begin. We start putting the green dots down, the green dots. The green dots. And if you're colorblind or color sensitive, just do something else. Use some kind of code. The green dots are meant to go inward and upward on our shell. The green dots, you have lots of choices here. You could connect it to the blue with three, or you could connect it to the red if you want. That's okay too. The red is stable. The blue is stable now. You could do whatever you want, but you must have three struts per node. All right, so let me show this now. This node is stable because it goes, well, let me back up a little bit here. This node is stable because I went to blue, blue, blue. And the blue was stable because it went to red, red, red. Okay, these will be in the air later. This one is stable now. So the next one can use it. Stable, stable, stable. That's the rule. Three struts must touch previously stabilized nodes. They could be on the ground, They could be in the air. It doesn't matter. Next one, stable, stable, stable. Next one, stable, stable, stable. We have the minimum number of sticks needed to stabilize these floating nodes. Three times the number of nodes that are in the air is the number of sticks, and you can count this. I don't know how we would do this in Grasshopper exactly. I think there's some human judgment that has to happen. We'll worry about that later. After the green dots, let's get the black dots in there. How do you do that? Let's look at this one. Stable, stable. I chose here to go all the way down to the ground. Remember, the red is on the ground. Next one. Now this one is stable, 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 stable. Remember, all the greens were stable, all the blues were stable, and all the reds were stable. Oops, okay, that's not correct. See, that's not stable yet. You can't do that. Stable, stable, stable. One, two, three. One, two, three. I think that's it. Perfect. Now you can count the number of floating dots, count the number of sticks. Should be 3 sticks per dot. And I'm moving inwards. I will also be moving upwards. Okay. One more time. I think you get it, though. I hope you get it. There's only one rule. Stable, stable, stable. And I do sense there's a grasshopper sort of order here. Notice what I'm doing. Left, middle, right. Oops. Left, middle, right. Left, middle, right. Left, middle, right. Maybe it can be automated. This is just the beginning, and I don't want to just keep it random forever like this. I should be looking at the target, right? The target, the yellow might be out here at this point. All right, now we flip over to 3D, and now we think like builders. What goes up first into the air? The blue. The blue goes up in the air. The blue goes up in the air. What goes next? The green. The green goes up in the air. What goes next? The black goes up in the air. I did have a problem in GeoGebra. I think there's some kind of bounding box here. I couldn't lift these things up taller than some height. I manually changed it under the object properties, but I wrote to the chief technical officer of GeoGebra, so we'll figure that out later. Now everything's up in the air. Um, Is this structural art? No. Is this a final project? No. But the idea here is that it's starting to look like the AI image, and this did not take a long time. You have all day to work on it, and all night, every day, and every night, and weekends too. All right, now notice how we started this whole process. We started this whole process like this, a little bit random. What if we were thinking about aesthetics and thinking about the efficiency of structural load flow? How might we channel the flow going into the red supports in a structurally rational way? Something like Pierre Luigi Nervi would have done. Something like my main man Myron Goldsmith would have done. How does that work? Well, we generate load flow diagrams. We could use our imagination. We could use our engineering intuition. We could use stress maps from finite element programs. We could use the Airy stress function. We could use magnetism. We could shake a table full of salt and see what happens when the plate is vibrating. Look that up on YouTube. That's mind-boggling, those shapes that happen from vibrating plates with table salt. But anyway, we're not just random anymore. Maybe we have the black blobs being our foundation, and we have flow going to the foundation, and we even have an oculus. How cool is that? Woo, that's cool. All right, so then you start putting the blue dots on your stress trajectories, your load flow. Then you start tessellating 1, 2, 3, 1, 2, 3, like we did before, to stable points, which for us will be these blobs. These blobs are our stable points, right? So we start by uh, connecting the blue 1, 2, 3, 1, 2, 3, because that one's stable already. All right, et cetera, et cetera. At this point, you could talk to AI again and say, what are we looking for? We don't want any orphan lines where, where is this going? It's not going anywhere really. Maybe there's a wall. But you need to think about that. If it's a free edge, you need to think about that. Like if it's a free edge on our structure, there's no force perpendicular to the edge, but there is force parallel to the edge. Of course, the force cannot be perpendicular to the edge because there's air out here. Who's going to stop it? So it flows parallel to the free edge. You need to start thinking about load flow like water. Where's the water going? If I pour water on the shell, where is it going? It goes to the foundation. How does it get there? That's you. You decide how it gets there as the designer, as the structural designer. This is structural rationalism. All right. Can you improve these patterns? Yes. Will you improve these patterns? Yes. Does it have to be grasshopper crazy attractor points? No. Are grasshopper attractor points really a good idea? Yes. What about something like this, where you take it, flip it around, mirror it, superimpose the image? Whoa, that's nice. Yeah. Yeah. Can you do that? Yes, you can. Now, what do you do with this? This is interesting. Do we put a dot on every intersection? Maybe in Grasshopper, maybe that's what we do. Um, do we control the coarseness or the fineness of this mesh? Yes, maybe in Grasshopper, that's something we do. For the purposes of this workshop, though, we're not going to use Grasshopper, but if you are good at it, I encourage you to explore that. We will be doing this in GeoGebra, putting the dots down, starting with the red dots around the perimeter of our structure, then the blue dots, then the green dots, et cetera, et cetera, et cetera, and building it up manually. If you can automate that with Python, fantastic. Then remember, they go up. They go up. You control that. I'll show you how to control it later. But the workflow is this, that you go to the robot for visual cues, but this is a picture. It's not a 3D model. Can it export STL models? Yes, it can through Python. Are they good? No, they are not good. All right, so hopefully that's a good overview of what we're going to do, and start thinking about Grasshopper or other automative tools. Sick miss, good luck.